over this notes, and then we went over it as well. I'm going to just skip through notes today. Oh, wrong. Here we go. Wrong 9:30 class. We actually ended up over here talking about the metric system, okay? Now, I'm going to skip this for a moment, and then I'm going to skip this. I will come back to this on Thursday, but again, it's the metric system. And what did we talk about? The 7 base units. What did I call those 7 base units? The parents. Remember, out of those 7, all other units were what we call derived, or they were made. How did they make new units, Miss Munson? These 7 units were either multiplied or divided with each other, and that's how they made other units from those 7, okay? Then again, here's the prefixes with conversions. I know it looks easy cheesy, but it's really what we're talking about, this unit. I want to start here. Accuracy and precision, because this is going to be on some of our homeworks, and so we definitely need to have our notes done on this. Accuracy and precision. Now, are the words accurate and precise the same exact words? Heck no. Do they have a difference between them? Yes, they do. They are 2 different meanings, 2 different words. Now, unfortunately, though, a lot of people use these words interchangeable, like that tomato, tomato. But unfortunately, they are not the same thing. The word accurate or accuracy is how close the measured values are going to be to the actual true value. Like, what is the actual number? Or we call this the degree of correctness. The degree of correctness. So let me give the example here. My example for this one is, have you ever got sick and maybe you had the flu, or you had maybe strep throat, or maybe you had both, I don't know. But they go in, they do a little swab on your throat with the nurse, they leave, and they come back and they tell you, right? You definitely want to make sure that that test is accurate, right? You don't want that test to not be accurate. It needs to be as close as the exact value as possible. I don't want that doctor or nurse messing up my values and telling me incorrect test results, right? Let's look at the word precise. Precise is going to be how close the measured values are to each other, or how consistent they are. Well, let me give you this example. I don't know how many people played baseball or softball, for an example, but precision would be kind of like that one kid who keeps hitting those foul balls over and over and over and over. Or they keep hitting the ball to left field, you know, down the third base line or something like that. So everybody scoots over because they know that ball is good, because they're very precise. They know that's exactly how they're going to hit that ball, okay? So looking at some actual practice problems. It says over here, well, what if we have some bullseye? Decide if it's accurate, precise, or neither, okay? Now, those values are not even close to each other, but they're touching each other. I tell my students, and I know every teacher is probably a little different when it comes to this, because I do work at the hospital lab, we like to look at values quite often and compare those values. It's important that our tests are completely accurate when we're resulting lab results. Now, in my mind, I say the majority rules is my overall answer. One more time, majority rules. And if they are touching each other, or if we're looking at actual, like this chart right here is number values, if they're one number off of each other, like if the smallest number is going to be the 100th place, and they're a number off of each other, I call that precise because they're like touching each other, okay? These are all touching each other. Over here, I only have 2 that are touching each other. And then over here, snap, all of them are touching each other. Like, that's really good. I can also see those are touching and those are all touching. I can also see that in the middle one, we have the bullseye. Don't get me wrong, that's pretty awesome. If you were playing this game of darts with somebody and you touched inside of that bullseye just a little bit, you would have got the point. But look at this one. Not only did they get in the bullseye, they got smack dab close to the middle, and they're all touching each other's values. That's really great. So over here, because all of these also are all touching each other, we have some great precision. I'm not saying you're accurate, but you've got good precision. On this side, I've got great precision. Those are pretty nice. Going back to the first one, I know I skipped the middle. Let's look at accuracy. I can definitely say not accurate. Not even there. Not accurate. There is no accuracy. Not accurate or no accuracy. I'm going to skip over to the last one, snap. Not only is it accurate, it's not even okay accurate. This is some great accuracy. That's pretty good. Man, I need you on my team. But let's look at the middle one. Again, I like to call it majority rules. Number one, I've got 2 values that are touching, and if there's 5 values there, I would at least need 3 values for the majority rules. So I'm going to just say it's meh or okay precision. Like it's not great, it's not good, it's okay precision. It's going to be that meh emoji. But let's look at accuracy. It's meh, okay, it's not great. Again, this is pretty great. This one, it's okay. Accuracy. And the reason why is because, yeah, they're right there on the edge, but man, can we see that there's even a better way to get this point value, I guess? This is even better than this. This is okay. That's great. All right, so we'll come back and look at that one later on, Thursday. This section here, like I said, I'm going to be skipping around a lot for today. This section is graphs. I'm about to turn the page in just a moment. This section is going to talk about, hey, don't forget the X and Y axis. Make sure you title your graphs, title your X and Y. That's all this section is. I want us to get into a little bit deeper on physics graphs. And so because of that, I'm going to go to this page. This is really starts our first part of physics. This is kind of like your first step into physics. Now, before I do this every single semester, I stop and say, hey, do you remember biology class when you took that? Your teacher probably told you all things are going to be biotic or abiotic, right? Like we categorize it as living and non-living. And why do we put things into categories? Well, because it's easier to remember. Now, in chemistry class, okay, let's stop and think about chemistry class. Ions, all ions are going to be either cations or anions. Unless you're a noble gas, then you're not going to be an ion. But you're going to be a positive value or a negative value. Pretty, right? Pretty easy cheesy. Okay, I got you, miss. In physics, all things are broken into 2 categories. They are going to either be scalars or vectors. Scalar or a vector. Okay? Now let's talk about what those words mean, because the meaning is going to determine what the answer looks like. There you go. So on a scalar, it's going to be a quantity that has magnitude only. Magnitude only. A vector has not only magnitude, but it also has direction. Kind of like on that Minion movie. I don't know which one it was. There's one guy, he said he was a bad guy. His name was Vector because he has magnitude and direction. There we go. So scalar is magnitude only. Now, I want to come over here just in case if somebody says, well, they don't want to raise their hand, but in their head they're saying, I don't have a clue what the word magnitude means. All right? The word magnitude means amount or a number. That's what the word magnitude means. It means an amount or a number. For an example, the mass is 16 grams. It has a number, an amount, but remember, because we're in science class, we always have to add an SI unit. So a number and an SI unit. How about the next example? We've got 14 students in class. We have a number, an amount, 14, and the word students would be that SI unit. So that way we know what we're talking about, 14 students. But wait a minute, a vector would be 14 students going to the bathroom. That would give me the direction. And direction does not have to be only north, south, east, or west in physics. We actually use directions like I'm going to Walmart, I'm going home, I'm going to school. Look at this. I'm moving forward. The object is going backwards. Okay, those are directions. Okay, or how about this? Kind of like math class. It's moving in the positive direction. What would positive direction be? Up or to the right quadrant, right? Same thing here. You're going to see how your math class really correlates with physics. Or the object is moving to the negative direction. Negative direction would be to the left or down, okay? So that's what we mean when it comes to magnitude or magnitude and direction. Let's take a glance at the definition or the word motion. Motion is any movement or change in position. Any movement or change in position. Well, the next word is going to kind of help us a little bit because how do we know that we're moving positions? Well, it says here, we know that the object is moving when an object changes its position with respect to its reference point. Now, an easy way to think of reference point, we say, is going to be the background. Like, for an example here with you, it would be like your desk, your table, your chair, okay? Those would be considered like reference point. Your backpack, your drink on your table, those are going to be your reference points. The background of what's around you, your surroundings. So one more time. How do we know an object is moving? Because if the definition of motion is an object that is moving or changing positions, well, how do I know that it's moving or changing positions? Well, with respect to the background objects or to the reference point, that's how I know it's moving. It says over here, what about that old school Marios? Like Nintendo, like the first original one, right? Mario is sitting there, he's jumping up, or he's moving his legs and arms like this, like if he's moving, okay? But truly, he's not moving on the screen. He's really being still. It's the background of Mario that you're able to see that that is moving, and it looks like he's moving. But a long time ago, these Nintendo games had horrible graphics, right? We weren't like doing the kind of coding that we're doing now or had the technology. And so for situations like that, the object is moving if it's moving against the same background. So for an example, that Mario, looked like he was moving, or to our eyes, it looked like he was moving, because that background stays the same or it moved behind him. Okay? Let's keep going on that one because sometimes that's a little tricky. It says here that stationary backgrounds are going to be called the frame of reference. And that would be like, for an example again, the desk, your chair, your water bottle, your backpack. Those are stationary objects that are not living, that don't have feet and can't get up and move by themselves. And so in reference to the desk or chair, you're either moving or not moving. Okay? So it says here, determining if an object is moving depends, and you need to consider their background. Again, there as in that object that you're talking about's background, or their frame of reference. That's it. Their background or their frame of reference. So with that, the next question is, so are you moving or are you not moving? Brooks, are you moving or are you not moving? Give us an answer. Don't tell us your frame or your frame of reference, but tell us, do you consider yourself moving or not moving? Brooks is moving. I mean, and if Brooks's frame of reference is a good, valid one, I can't argue that. What's your frame of reference, Brooks? You ain't walking though right now. Give me another frame of reference. Can you think of a frame of reference, Okosa, of why he's moving? Because if he says he's moving and he wants to be right, let's make him right. Okay, his hands are moving in reference to the paper, and that paper is a non-living object and it can't move. Travis, can you go even deeper? Can you expand that even better? He's moving. I agree he's moving. Can you give me something else? I mean bigger. Give it to me.
I was thinking when it references the sun.
Ooh. In reference to the sun, not only is Brooks rotating around the earth, right, because we have to have night and day, but then the earth moves around the sun 365 days so it can make it back around, because this time next year, most of y'all are going to be seniors, all right, y'all getting older. Not only that, but our galaxy is continuously expanding. We are going to get to the point in a few hundred years we are no longer going to have eclipses, believe it or not. We are going to be so far from the sun because everything's expanding that whenever the moon goes or the sun goes in front, it's going to be too small. We're not going to have like a full eclipse. Okay, full eclipses or total eclipses are going to be gone. Imagine thousands of years ago on when people went outside at night how it looked, because we were closer to the sun. Planets were closer to each other and they're moving further away. That's crazy to think about that. But we are continuously moving. So if Brooks says he's moving, I'm not going to argue with Brooks. Brooks, you're moving. As long as you tell us what your frame of reference is. Okay, now if you're not moving, then maybe your frame of reference is your desk. Like, Miss Munson, I'm chill right here. I don't want to get up. I'm just going to hang out right here and sit down. I'm not moving. And that's A-okay as well. Because we know that the earth is always moving around the sun at a rate truly of 18 miles per hour. Not only that, but it's spinning on its axis from night and day at about 1,000 miles per hour. That's a lot. So that way we can get into night and day every 24 hours. You can be considered moving. And I'm okay with that, as long as your reference point is correct. It says over here, well, why don't we feel like we're moving fast, like a roller coaster? Because if you're spinning on the axis of the earth, and the earth is rotating around the sun, and the universe is continuously expanding, why don't you feel like you're moving so fast? Because your reference point is your table or your backpack. How fast is that moving? How fast is your backpack moving, Acosta? Your table. Is it moving? But is it really? So I don't know about you, but I will tell y'all, I do have a fear of, I have a fear of roller coasters. Can't get on roller coasters. Save my life. I'll cry. Literally, you want to see me break down and cry? Put me on a roller coaster. They move too fast. In reference to the people on the bottom, in reference to like a tree or something, roller coasters, I feel my body shaking and moving, and I'm scared. I really do get scared on roller coasters. But right now, you're moving as if you're on a roller coaster. That's how fast up there on letter A, that's how fast you're moving. But I don't feel like I'm on a roller coaster right now. Actually, I feel like, just standing here. But that's probably because not only are you moving at this speed, but because everything around you is moving at the same speed. And because everything around you is moving at that same speed, it feels like I'm not moving. Because we're all on the same roller coaster together, right, here on Earth. And so it doesn't feel like it. I don't feel sick. I'm good. I'm going to leave this page for a few more minutes, or a few more seconds. Then we're going to turn the page in a moment. That's why. Okay. Again, don't forget, I like to record these lectures just in case if somebody's absent. And then after class, I'm going to go scan these and post them on D2L. You probably saw last week's video was posted. So I like to do that just so that way we can stay on top of things, just in case if you're absent for an activity or something. Okay, I'm going to turn the page to this section. I want to talk about the word velocity and speed. And then after that, we're going to color. That's what's going to happen. Okay, so for velocity is one of our easiest equations. I also pulled out our equation sheet, and I will post this on D2L. But here are the equations that we're going to cover this school year. And we're not going to cover all of them. Don't freak out. Okay, we're going to cover most, but not all. All right, let's talk about this first equation. Velocity is our first equation. Now, one thing that I will tell you all school year long is that velocity is going to be a vector. Remember that word? A vector is a quantity that has magnitude and direction. But don't forget, all magnitudes need an SI unit, or minus 2 points. All right. So the definition of average velocity is an object's displacement over the period of time that it took it to move. The object's displacement over the period of time that it took it to move. The equation is velocity equals displacement, and that's the true definition, over time. Right? If you're missing a variable, all you got to do is algebraically solve it. Or for those of us who like to use the triangle method, that will be your fast way to solve this algebra problem. V equals D over T. But your answer is going to look like this. It's going to have a number, right? I don't know, 16, 22, 3,000. And an SI unit. Now I'm going to pause here. I'm going to scoot this over because I need to look at this algebraically. What's a simple, easy, cheesy SI unit for distance? Why not say meters? Let's say meters. What about time? Well, in physics class, we're probably going to use seconds. But if it's not, we can always convert or just leave it as is. No freaking out on that. We don't want to convert if we don't have to. Algebraically, Acosta, can I cancel those two variables out? Are they the same? Or are they different? What do you say? M and S. They different or the same? Different? I was picking on you. You're so sweet. Different. So what happens with the different ones? I cannot cancel. Thank you, sir. I cannot cancel. Meters per second. That's what, so it would be a number plus my SI unit, which for an example, this would be meters per second plus a direction. Now that would be the physics correct, blah, blah, blah way to give your answer. I know, it's such a long answer. Now we're going to not do those math problems just yet because I want to look at VT graphs and we're going to look at graphs like this in just a moment. Okay? The next one, when we turn the page, when you're ready, turn the page, we're going to turn the page to speed. Okay? To speed. Now the definition of speed is going to be the distance. Oh, wait a minute, Miss Munson. Didn't you just say that velocity was displacement? Isn't that like a movement? It is, but correct, the physics correct way for speed would be the distance an object travels over the amount of time that it took for it to travel. Speed tells me how fast an object is. It doesn't tell me really the direction. Because of that, speed is a scalar. Speed is a scalar quantity. Let's go back. A scalar has magnitude only, which means the amount. So looking at this, speed, it's similar to velocity. Velocity truly is displacement over time. Speed is distance over time. My shortcut abbreviation would be D over T, right? And then again, if I was to say, let's just say centimeters over seconds for my units, I can see that they definitely cannot cancel out because they're different units, right? So I would have to keep both units. My answer would be some kind of number, for an example, centimeters per second with no direction. Okay? This is truly our first step into a little bit of physics. Okay? So speed and velocity. One more time. I'm sorry. Yes, speed and velocity. Speed is a scalar, velocity is a vector. Speed is distance over time, velocity is a displacement over time. But the word displacement is kind of like distance. Like how far did it move? We're going to talk about the word displacement on Thursday. Okay? Now, just to kind of like, we're going to slow down from all this note taking. We are going to actually go to this graphing paper, or this graphs over here, not the back one. But we're going to start here, where it says distance time graphs. Now, we just saw the distance and the time equation. And what is the distance time equation? This is going to be graphs over an object's speed. This is speed graphs, okay? This is going to be speed graphs. How fast is it moving? Now again, don't forget it is a scalar. But the cool thing about actual graphs, and that's what we're going to do this week on Friday, we're going to break up into groups on these computers, find a buddy, and truly I think 3 people would be the easiest way. So if you can find maybe a couple of partners, like I said last week, to kind of take a glance at them, give them a little wink, and let them know, hey, I'm going to need you to be my partner this Friday, all right? I try to let you partner up as much as you want to. I don't want to but into your partnering business, okay? But when we look at our graphs on Friday, which we're going to have to continue it on Tuesday, we just won't finish, not a problem. We are going to see graphs like this. The crazy thing is that when I learned this, there was nothing to simplify it. It was just like memorize. And you know what? We are going to memorize. But before we memorize, I want to simplify it and color code it. So that's where my colors are going to come in, okay? Because I want to really try to help you out. We're going to use pink, then blue. Oh, wait a minute, not yellow. TC Sting, and then green, okay? That's what we're going to go in those orders. Now, when it comes to DT graphs, they can do 4 different things. Here's my X and Y. This is my distance and my time. Distance is on the Y-axis. Graph 2, distance and time. Graph 3, distance and time. And then graph 4. The other graph is going to have 5 things that it can do. All right? So here are my DT graphs, which is which equation? Speed equation. A speed is a scalar. It tells me the distance that it traveled and how fast it traveled. That's it. How fast is it? All righty. So there are 2 things, or 4 things in total, but when it comes to my pink, we're going to start off with my object is what we called at rest. Those are like the physics terms, but let's use regular terms. It's stopped. It's not moving, okay? Well, what happens when an object's at rest, graph-wise? It's going to have a flat horizontal line with no slope, but this is the key thing. It can be above the x-axis, it can be on the x-axis, it can be below the x-axis. One more time. On a DT graph, which is a speed equation, my object, when it's at rest or stop, is going to have a flat horizontal line. It can be above the x, on the x, below the x. Okay? Next one. Number 2. On number 2, this situation is when my object is moving at a constant speed. And when it's moving at a constant speed, going on blue, okay, it's going to have a slope, but it can have 2 different types of slopes. It can have an upward slope, or it can have a downward slope, okay? An upward slope or a downward slope. This upward slope tells me that my object's moving at a constant speed away from the origin or away from home. In physics, we say away from the origin. Same thing, away from home. But if it's a downward slope, it's moving back towards the origin or back towards home. Okay? One more time. A nice pretty slope up or down. Okay? Next one, number 3, orange, when you're ready. This one is going to be when my object is going to speed up. Now, it can look like this, or it can look like this. Again, the first one means that it's going to speed up away from the origin, or the second one is back towards the origin, okay? It's speeding up. The last one is green. Okay, so at rest, constant speed, speeding up. Last one is slowing down, as in you're hitting the brakes on your car. This situation, you're going to have a graph that's going to curve this way or a graph that curves this way. Again, the first one means that it's moving away from the origin, and this side means that it's moving back towards the origin. Okay? We're going to color again on Thursday. Yes, sir.
I don't think I understand the back towards speed up line.
Okay. Okay.
It looks like the same to me as the slow down away line.
You know what? It does to me as well. But let's look at these two. This one curves up this way. This one, if you were to flip it, inverse it, flip it, it goes this way. Does that make sense? This one, if it was a... How do I buy some more chords? So, this is a good example here. So let's say it's kind of this way. Does that kind of look like that? Flip it this way. This is away. Speeding up. This is away, slowing down. This, look at it now. This is going back towards the origin, speeding up. Flip it. It's moving back towards the origin, slowing down. There you go. I guess think of it like this, kind of like an object, like a banana. Like a banana. Here it is this way, flip it away. Here it is this way, flip it that way. I know, it's a little tricky. If I don't like note cards. I'm not a note card person after all these years. I figured that out. This is one of those ones that I would probably put on a note card. I don't suggest doing note cards I'm not like one of those biology classes or anatomy classes where you're like note card practicing. You know, this one, I would probably put those on note cards and be flipping through them every single day before we take our test. This is what throws my students off. And if you like to color code it and you figured out your color coding system, then I would color code it on the quiz and test. Have your highlighters and markers with you, if that's the situation that you need. No worries at all. All righty. Now, here's what I was taught. I was taught without that, and I was just taught, hey, this is what it looks like. Boom, go for it. So now I'd like to teach it as, hey, let's break it up. Step number one, let's go back to the pink. What was step number one on a DT? It was a flat horizontal line. Let's go ahead and let's color everything pink that you see a flat horizontal line. Like I'm about to simplify this to make it so easy for you. Okay, there's not a flat line on letter M. There's not. And not on K. Nope, not on K. There's one more. It's not A. It's not M. It's not N. Where's it at? Not C. We did D. Right here. That one was tricky. Okay, there they all are. I'm going to do this whole page with you. Then on the next page for Thursday, I'm going to show you, and then I'll let you do most of it on your own. Blue. Blue was the second one. Those are easy, right? Those are nice slopes. For an example, letter B, a nice slope. Letter E, a nice slope. Letter L, the whole thing is one slope. Letter H, a slope. Letter K, a slope. But look at letter F. Not only one slope, but two slopes. It's like slope, slope. It just does that little quick turn. Okay, we did all the blues. Let's go to orange. And again, those are a little weird looking. Those little like curved bananas. Okay? I definitely am going to tell you letter D curves up, like that first one that we drew. Letter N curves up. Letter M, I'm sorry, that was H. M and N curves up. And then our last one is green. Our green is going to be like the upside down, like facing down. You can see this one is facing down A, facing down C, facing down D, and then K also has a little facing down. All right, the next step. Now that we've got this color-coded, we're going to go back to the top of the words. And at the top of the words, we're going to start with pink. Oops, here you go. We got all that. We're going to start with pink. And remember, it's going to be at rest. And so anytime we read the words stop or at rest, we're going to color it pink. Let's do that. Number 1, at rest the entire time. Number 2, and suddenly stops. Number 4, slows down, comma, stops. Number 8, and then stops. Number 9, gradually slows down to a stop. And number 11, suddenly stops. Just comes to a stop. Let's keep going. If you feel like you understand this now, what we're doing, color all of the blues, the orange, and the greens. I'm going to color mine, you color yours. Constant, anytime I see the word constant. 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 Oh, whoa. 10, constant. 12. Not only is it constant, but it's multiple constants. All right. Orange. Anytime it says speed up. Speeds up. Speeds up. It speeds up the whole time. 11 speeds up. And then we're going to end it with green. So you do yours, and I'm going to finish mine. Slows down. Gradually slows down. Let's see. It slows down, then comes to a stop. Then gradually slows down. Okay? So get them colored in. I think I have mine colored all in. Looks like it is. And then we're going to match. I don't know about you, but I would much rather match colors instead of having to memorize something. Okay? So let's look at the big picture. I'm going to zoom out. And when I zoom out, on number 1, it's pink the entire time. Is there a graph that's nothing but pink?
Yeah.
Oh, there you go. I'm going to simplify this. Oh. Okay, let's look at number 2. Blue, then pink. In that order, B. Oh, whoa, is it B? No. Oh. Okay, I'm going to scratch it out. I'm going to go to number 3 then. Green, A. Green, pink, and orange. Green, pink, and orange. D. I mean, this is not bad. This is good. That's good. Constant speed. 7, blue. L. I'm going to jump down real quick to 12. Do you see that multiple constant speed? And then what matches with that is letter F. There's multiple blues. Multiple blues, multiple constant speeds. I mean, we couldn't get any easier, cheesier than this. The problem is number 2 and number 8. What's 2 and what's 8? What's 2? It's not B. E. Oh, okay, sorry. Absolutely, it's E. And the reason for that is because number 8 says it moves towards the reference point. So number 8 has to be this line where it's the downward slope moving towards the reference point. I agree. So we're using those keywords. I color code it. We're going to do a little color coding as well on Thursday. Okay, so I'll have the markers up here again. We actually finished about 10 minutes faster than the last class period, so we're good. If you need to print something out or get ready, you're more